Hey guys, what's up? Eddie Alho here with KissAnalog.com. Today I want to talk about power supplies in general, some terminology and some details and what we're going to cover. We just recently started a series on the boost regulator and we're going to cover that in detail, and then we're going to cover the buck, and then we're going to do the buck boost. I think those converters are all DC to DC converters, okay? So if you're a switching power supply guy, or a power supply guy in general, especially a switching power supply engineer, and somebody says, hey, what are the two kinds of power supplies? You may say, well, there's DC to DC converters and isolated converters. So basically non-isolated or isolated. So that's one way to categorize them. There's a lot of different ways to categorize things. We like to categorize things, but none of them are really definitive. You know, the definitions between these things, for instance, isolated converters, they could both be linear, what we call linear converters, linear power supplies, big old behemoths like this, and this guy here, linear power supply. We call these linears. I believe actually all of these are linear power supplies. Then there's the switchers. But when you say these are linear power supplies, it kind of puts them in a category, but it's not 100% correct, because when AC voltage comes in here and you convert that to DC power, then those diodes are turning on and off, so they're actually switching devices. They're directing current flow or voltage flow certain directions, so they do cause some spikes and some noise, so they're not quite linear, you know. But that's what I'm talking about, terminology. Now, when we talk about these linear power supplies, you know, loosely termed, these things are heavy, right? Big old heavy transformers. So what does a transformer do? Provide isolation. Well, there's another category we talked about, right? Isolation. So you have isolated power supplies, non-isolated power supplies, like this one. In isolated power supplies, you could say, well, this linear power supply has a big transformer, it's isolated. And a switching power supply, we have forward converters, flyback converters, bridge converters, there's others, and they also have transformers that provide isolation. So we just want to kind of talk about why these things exist and what's the difference between them. Well, on that topic, this big old behemoth guy here, he's heavy. His biggest problem, he's heavy and he's large. So a switching power supply, if you want to have a portable device, you want a switching power supply. Switching power supply is lighter. And why is it lighter? How come a switching power supply can be smaller and lighter than these big old boys? So basically the secret is the switching frequency, right? Not a surprise to a lot of you, but you know, really, this guy runs off 60 hertz here in the States. You know, other places 50 hertz. There's also 400 hertz, and there's other frequencies, but those are common ones. Those frequencies, as the voltage slowly moves through those cycles, you charge capacitors and you magnetically couple primary power to secondary power. Well, if you can switch that faster, say 400 hertz or 400,000 hertz, then you can switch a lot quicker. Your magnetics can get a lot smaller because the energy in the magnetics is a function of the frequency. You know, just like the X of L formula, 2 pi FL. So F, if frequency goes up, X of L goes up, keeping everything else constant, right? So when you have a switching power supply, you can make your magnetics smaller. It's like if you have a lot of people standing in line with water buckets. If you have a bunch of big old guys carrying big old water buckets, slowly filling them up and grabbing the next one, you know, that's kind of a 60 hertz cycle theme. If you have a lot of people switching hand cups real fast, you have a lot less water in each cup container, but you're passing on the same amount of current, right? Same kind of water. So switching power supplies, you can pass the same amount of current, but you just do it in little chunks. And so your capacitors, your containers get smaller. So you don't have to have these big old containers that only a big old muscle guy can carry. You can have these smaller containers, these smaller capacitors, these smaller inductors that can transfer the energy. So transformers, the coupling is, you can get the same kind of coupling at a higher frequency so they can shrink. So transformers get smaller. Negative drawbacks. Well, everybody's worried about switching spikes, right? These linear power supplies, the diodes actually cause some pretty high spikes. They cause some noise problems too, but they're big, so you can have, bigger parts and easier to filter maybe, but they're big. In a switching power supply, you want to keep things small, but then you have to add parts for these switching spikes, which we're going to show how to do that too, LC filters. There's also a different way to switch things, how you turn on and off FETs, how you can make those softer. There's a resonant type converter, which it's almost sinusoidal, and those things are soft switching. So when you talk about soft switching, you don't get these hard transitions, okay? And you don't get that noise spikes. But anyway, we're going to cover a lot of those kind of things. We want to just talk about, some of this terminology. If somebody says, what are the two kind of converters? I often, just say, well, there's IC converters and there's non-IC converters. There's a lot of designers who need a 5-volt converter, 3.3 or 1-volt converter, and they use a DC-DC converter from, a Vicor or Maxim or Texas Instruments, Intersil. All these people sell these DC-DC converters, and you'll plop them down and maybe have to design an inductor, design a few things, and you have power, okay? But if you need an IC converter, isolation, well, that's a little more difficult to design. And that's why we're starting off the boost. Not because it's the easiest one, just because it happened to be in my hand. But I think it's a good one to start with. So we're going to start with the DC-DC. Now, that brings up another thing. If somebody says, what kind of two converters are there? Well, you could say, well, there's AC to DC and DC to DC. Well, that's kind of true too. Those are two big categories. AC to DC, big old linears we're talking about, bringing AC power in, convert DC. If you're bringing in, say, 28 volts and you want to make 5 volts, 3.3, all these low voltages, you can use a transformer to isolate that and provide isolation from your primary side. And also, even though you're bringing it from a DC side, you don't have the AC power, safety issues. You still have things where, hey, you don't want to, let's say, short an output and bring your prime power down. Say in a car, 12 volts. You don't want to short audio amplifier and bring your, stereo down. Well, you have fuses and all that kind of stuff to protect that. But another protection mode, and also for noise, is to have a transformer there for coupling, for isolation between primary and secondary. Brings on a bunch of different ways. There's also ways to define power supplies. There's also inverters and converters. An inverter is, you start off at DC, but you want to make AC power. A lot of cars now have inverters built in to provide AC power for those products that want AC power. So inverters or converters. Converters are just typically thought of as DC to DC or AC to DC, but inverters are DC to AC. You see? So there's, when I talk about power supplies and that, I might use a term that seems out of place because, depending on where you're standing, the definition can be, not as definite as it might seem. So I'm just saying that there's a lot of terminology and a lot of ways to categorize things. And so sometimes, if there's any questions or anything like that, comments, please comment always. I love you guys commenting. It helps me a lot. So some of the terminology in these power supplies, switching nodes, okay? First of all, pretty much regardless of whatever kind of power supply you're talking about, unless it's a linear power supply maybe, but any kind of switching power supply, you know, people are worried about noise. On these linears, you know, you have this power factor problem too. If you're creating DC from an AC, you have 60 hertz, 400 hertz, whatever is coming in, and then you go through a diode bridge rectifier, right? And then a transformer. And you maybe have one of these big old toroid transformers for audio. Awesome. Toroids are, well, more terminology. This is a toroid. Some people call them, well, sometimes I call it a donut. So a toroid is just this donut shape, okay? So that's a toroidal, or toroid magnetic is. Which brings me to another point, magnetic. Whenever we talk about magnetics, it's inductors, transformers, anything wrapped on a core, any coil, any inductive term, transformer term on your schematic would be what I think we would call a magnetic, okay? So those are great. Now, what if you have three-phase power coming in and you have a power factor requirement? Well, you might feel like you need to go through some kind of fancy switching topology where you can control that power factor and try to keep it clean. Well, so if you don't care about weight and you're like in an industrial area where maybe you have the size, well, instead of going to a switching power supply with some fancy type of topology, which there's another term, topology. When people talk about topology, they're usually referring to, you know, as a, you know, what your schematic generally looks like. Does it fit a boost, a buck boost, flyback, forward, you know, bridge? That's the topology. And so with an AC power supply, if you need to have good power factor control, good quiet, good low harmonic distortion kind of requirements, well, you can use a multi-phase transformer. What we call a multi-phase, that's where you can bring three-phase in and come out with 9-phase or 12-phase, 15-phase. And it's really an interesting way they do that. And they take the different phases, wind the transformer such that you get these other phases. It's really cool how that's done. And when you do that, you get good clean power factor and good clean harmonic distortion, or very low harmonic distortion. So that's another way to do it in a linear fashion. You know, you have a lot more diodes. Each diode's conducting or commutating, and there's not this strict on-off cycle you get with the normal bridge rectifier. So multi-phase transformers are great. A great solution. Robust. You don't have a lot of semiconductors and control circuitry and stuff like that to go wrong. It's just passive, drop in a gigantic transformer, and away you go. So a lot of different ways to handle things. So I just wanted to bring up all the different kind of power supplies there are. But when we're talking about switching power supplies, we'll generally have a control chip. That control chip is the thing that's switching your main FET that's turning on and off. So you have DC power coming in, and you want to create not 60 hertz, 400 hertz. You want to create, say, 100 kilohertz, 800 kilohertz, a megahertz, you know. And so you switch real fast, and that it's creating that on-off cycle that lets your transformer, your magnetics transfer energy. So when you do that, you have this control chip that controls that FET. And why does it control? Because it's looking at the feedback of the output and determining how to control that FET to regulate that voltage. A lot of times it's fixed frequency, say 100 kilohertz, and you're going to adjust that duty cycle to keep that thing regulated. Okay, so that control chip can also look at the current pulse by pulse. Each time it turns on and off, it can look how much current that's been drawn, and pulse by pulse, which is a big deal, you know, because it reacts so quickly, right? 100 kilohertz, you know, so you can watch that current, each pulse, and if it goes above a certain amount, you go, whoa, might be a problem here, and you go into current limit. Okay, so that control chip can take care of your current, your overcurrent conditions, your voltage regulation, and it's all the while controlling that switching FET. All right, so you got a control chip, you got a switching FET, and so typically between the switching FET and some magnetic, there's a switching node. There's a node that is, it's a junction between these parts. We call it a node, and that node will be being pulled from one place, say from a high voltage to a low voltage, on off. Okay, that's your switching node. All right, so you got your control chip, your switching node, your switching FET, and then you have this other device that's going to transfer power, and that's often called a Schottky diode. We use Schottky's because they have a lower voltage drop than a normal diode, say 0.4, 0.5 volts versus 0.7 or 0.6 of a silicon diode. Okay, so Schottky diodes are great for that. There's some other advantages we'll cover, but then you can also use a synchronous rectifier, it's called. So that Schottky diode's a rectifying diode. It's directing the current one direction, so that's the rectification, and you can replace that so you get a lower voltage drop with a FET, and now you have to control that FET on off. So, but that FET, the advantage of that, of course, you get a lower voltage drop than 0.4, 0.5 volts. Now you get even a lower voltage drop, and so an efficiency bonus. So that's usually tied to your switching node. Okay, and then another common part you'll find in power supplies, depending on topology, is you'll have a flyback diode. So magnetics, they don't want to switch, they won't switch current instantly. The current has to start flowing through a magnetic field. When current first changes speed through a magnetic field, that magnetic field increases, and it opposes that current flow, so it doesn't allow it to change instantly. So you build this big magnetic field, and then it says, okay, now I'm filling my energy up with this current, and it allows it to flow. And it's kind of like a capacitor. A capacitor, you can't change voltage instantly. Put 12 volts on a cap, it doesn't instantly go 12 volts. You're going to short that 12 volts out instantly, and then it's going to charge up quickly to that 12 volts. And then once it's charged up, now it's full of current, and the voltage is held steady. So, so magnetics and capacitors are both energy storage devices, and we use them in power supplies. We use both pretty much always. Maybe not always, like I say, definitions, right? But pretty much always. So what we do is we have a second switching element often in power supplies, and that is to let the current and that magnetic to continue to flow when that switching device turns off. When that switching device turns off, then this other switching element called a flyback diode, commutating diode, a freewheeling diode. It's freewheeling because it's just kind of hanging out, and then when all of a sudden it's polarized, it's saying, okay, I'll conduct. And so when that switching device turns off, then that freewheeling diode says, okay, hey, I'll let current flow through me. So it allows that magnetic to continue flowing current. Okay, so those are important parts of our circuit. And those freewheeling diodes are often switched to synchronous rectifiers because that's part of our rectification stage. But so anyway, so there's some terminology, there's some ideas, and just kind of a discussion about power supply. So I hope that was helpful and kind of fills in some blanks maybe on some of the terminology. Hey, one thing I want to kind of explain in a little more detail is when we say isolated power supplies, I think we're all on board, right? That's, you got primary power coming in, whether it's AC power or DC power, and then we're going through a transformer and we're sending out power, and that's isolation, right? It's like this guy. He isolates output power from the input power. And with that isolation, what we mean, I guess, definitions, is that it's galvanically isolated. That means you take an ohm meter from the input to the output, you do not have a DC connection. There's galvanic isolation. Alright? So just want to make sure that we're all on the same footing as far as, or definition as far as what isolation means. Okay? And then just a little bit of information about the control chips and how I talked about voltage and current. Well, it brings up another thing where just, some really common terms is voltage mode control and current mode control. So when I brought that, control chip, some people call them PWM chips, pulse width modulation, okay? Switch mode power supplies, SMPS. Those are just terms, okay? It's good to kind of know where those things come from. And so your control chip, or your PWM chip, your pulse width modulation, so the pulse width would kind of say, hey, we got a fixed frequency and we're changing the pulse width. There's other kind of control chips that handle the frequency or the control differently, but that's one kind. And within that type of regulator and other types, there's also voltage mode and current mode control. So the voltage mode will look at that voltage feedback, regulate the feedback. It'll still have current mode control in a sense where it can monitor current, and when it goes above a certain level, it shuts down. Okay. Difference between a current mode control and a voltage mode control is current mode control will look at the voltage. It pretty much does the same thing as what we just said for the voltage mode, but pulse by pulse, it's going to be changing the voltage reference for the output. It's going to be changing that with how much current's going through. So it's going to change the duty cycle based on current and voltage feedback. It's going to maintain that regulated voltage output, but it's also going to base that off of how much current pulse by pulse it's putting through. Okay, a little bit different in how that works in the control loop. Okay, and so we do have that feedback loop path, and it kind of changes that a little bit depending on that mode of operation. Voltage mode came out first, current mode came out later. So a lot of things are current mode control. Sometimes it's considered the better mode of control. Sometimes voltage mode is better. So anyway, just covering a lot of terminology here in this video, and I hope that helps. So let me know. Hey, please comment. Other people read these comments, other viewers, so it helps everybody. So hey, thumbs up guys, that helps me too. Okay, and thanks a lot for watching.